Hello everyone. Hope you all are doing well and enjoying statistical thermodynamics or statistical mechanics or chemical statistics. So it's time to derive the Boltzmann Distribution Law. In this context, we have to take a system where n number of particles are distributed in several energy levels which are discrete in nature or which are quantized in nature. If epsilon 0 is the ground excited state, its energy is 0. If epsilon 1 is the first excited state, its energy corresponding energy is epsilon. For the second excited state, the energy level is epsilon 2 and its corresponding energy is twice epsilon. And this way we can reach up to the ith excited state, which is the epsilon I energy level, where the overall energy is I epsilon. And the particles, the overall n number of particles are distributed in all these quantized energy levels, such as the ground state is occupied by n0 number of particles. These particles are classical particles or molecules. The first excited state is occupied by n1 number of molecules or particles. This way, the ith excited state is occupied by ni number of particles. One thing I must mention here, that these numbers are variable. n0 is a variable number, n1 is a variable number. This way ni is also a variable, but their summation, that means n0 plus n1 plus n2 dot 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 ni, that means sum over I ni equals to n, which is the total number of particles, which is in turn a constant. This total number of particles does not change. Okay, and if somehow these energy levels are degenerate, that means they have subshells or sub energy levels, then these numbers are denoted as Gi. This is the statistical weight factor or degeneracy. So if it is the ground state or ground energy level, then its degeneracy is denoted as G0. Similarly, up to the ith energy state, its degeneracy, or in general its degeneracy, is denoted as Gi. So this Gi is also very important here. Now let's move on to the expression of total number of particles, which is a constant. So this is n, is actually n0 plus n1 plus n2 plus dot 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 ni, which may be written as sum over I ni. Okay, now what is the total energy of this system? Total energy of the system is the energy possessed by all the particles of these systems. So the ground state energy levels energy is n0 epsilon 0, because there are n0 number of particles. Each particle has epsilon 0 of energy. So the total energy of the ground state is n0 epsilon 0. This way the energy of the first excited state is n1 epsilon 1. And similarly, the energy of the ith excited state is ni epsilon I. So their summation is sum over I ni epsilon I. This is the total energy E of the system. So this is the total energy E of the system. And this is also a constant. Okay, now the expression, move on to the expression of probability or thermodynamic probability, W. This W has the expression n factorial over product over I ni factorial. What is product over I ni factorial? This means n0 factorial into n1 factorial into n2 factorial into dot 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 into ni factorial. That means this is the product, this is the multiplication of the factorials of the number of particles in each energy state. So if natural log is taken in both sides, then in the left hand side we will have ln w, and in the right hand side it should be ln n factorial, and since this is a dividation sign, so it would be converted into negative sign minus, and this product sign would be converted into sum over summation sign. Okay, this product over I would become sum over I, because we are taking the log now. Suppose log of x into y into z, what is that? This is log x plus log y plus log z. So the multiplications are converted into summations if it is the logarithmic function operation. Okay, so it would become sum over I ln ni factorial. Is that clear? Now the Starling approximation. This we have done in my last lecture, the 4th lecture on statistical thermodynamics. So you have remembered the Starling approximation, which can be applied in both the expressions. Here in this expression, here ln n factorial. This is a large number now, so it can be applied. And here ln ni factorial, this is also a large number, so here also it can be applied. So in both these expressions, the Stirling approximation can be applied. So this can be written as n minus n ln n, and here this one can be written as sum over ni minus ni ln ni, sum over, obviously sum over ni ln ni. Okay, the summation sign would be put in both cases, but the Stirling approximation can also be applied here, such as sum over I ni ln ni minus sum over I ni. Okay, so this way we can apply this here, n ln n minus n, then sum over I ni ln ni minus means here it becomes plus because the minus sign is put here, so ni sum over I ni. Okay, so hope the Stirling approximation, application of the Stirling approximation is clear to all of you. Now the question is that what about this? Just it has been written that this is nothing but n, the total number of particles, and here also we have another n, this is minus n, this is plus n, so these two would cancel each other. But we should get, this is written here, n equals to sum over I ni, and it would cancel each other. So the two terms left are n ln n minus sum over I ni ln ni. Okay, now at equilibrium, this was also said at the time of discussion of probabilities. At equilibrium, what? Now this is maximum, so its derivative would be 0. Okay, so the derivative of ln w is 0, so d ln w is 0. If it is at equilibrium, then this expression's derivatives, the derivatives of the right hand sides also would become 0. Okay, so we can write derivative of the first term and derivative of the second term equals to 0. Now look at this term n, as I have said that n is a constant, so its natural log is also another constant, and n and ln n when multiplied with each other, then this is also produce another constant. Then what should be its derivative? The derivative of a constant term must be 0, so this term is also 0, and the negative sign can be merged with 0. So we can also write that derivative of sum over I ni ln li is 0. Look, n is constant, so d n ln n is 0. So we can write derivative of sum over I ni ln ni is 0. Now apply the rule dxy. What is dxy? Dxy is nothing but x dy plus y dx. Here also this one d this one and this one d this one. Okay, so and summation sign is as usual there, sum over I. Okay, so sum over I ni d ln I plus sum over I ln ni d ni. Okay, so this is also equals to 0. Now this can also be written as d ln ni can also be written as what? Now d ni by ni, and these two ni can cancel each other, so only d ni would be left here. Okay, so here we can write sum over I d ni plus sum over I as usual, this one as it was. Okay, but sum over I d ni is nothing but dn. Okay, and so you can guess that dn is another 0 term, isn't it? Here it is also written and this is omitted. So finally we have got dn plus sum over I ln ni dni equals to 0, and since dn equals to 0, we can write sum over I ln ni dni equals to 0. And this is a very important equation. This red colored equation or this magenta colored equation is very much important, and this is written as equation number 1. Okay, so remember equation number 1. What is equation number 1 now? Sum over I ln ni dni equals to 0. So we take this equation into account, and this can also be written as we have already said that sum over I dni, this is nothing but what? No? dn, and this is also 0. So dn is nothing but sum over I dni, this is 0. So we are considering this one as equation number 2, and this is a very important equation because this is also going to be taken into account. Okay, and this way we are going to have another equation number 3, and by the help of this 3 equation we would derive the Boltzmann distribution law. So equation 1, I repeat here, equation 1 is sum over I ln ni dni equals to 0, and equation 2 is sum over I dni equals to 0. Okay, now the total energy expression E is already, we know that sum over I ni epsilon I, and if we take derivative of both sides, then it becomes dE equals to d of this term. Okay, and since the total energy E is constant, as I have said that E is also a constant, so dE is equals to 0, so the left hand side is equals to 0, and that means d of sum over I ni epsilon I equals to 0. Okay, now again the derivative rule, dxy, x dx, x dy plus y dx, likewise this here, ni d epsilon I and epsilon dni, and some of our signs are as usual there. Now which term is 0, this one or this one? Can you say? As I have said, already said that ni is not a constant. N is a constant, but ni is not a constant because the number of particles in any energy state can vary. So dni cannot be 0 because ni is a variable term, while the energies are constant for each energy level. They are quantized and they are fixed. So epsilon I is a constant, so its derivative is also a constant, isn't it? So it is mentioned here that ni is a variable but epsilon I is a constant, resulting in d epsilon I equals to 0. If d epsilon I equals to 0, then ni d epsilon I is also equals to 0, then its summation is also equal to 0. So this part, this is the first term of the right hand side is 0, and the second term must have to be 0 also. Okay, so this one is 0, so this one also have to be 0. Okay, so this one equals to 0 is our desired third equation. And what is that third equation? Now the third equation is sum over I epsilon I dni equals to 0. This is equation number 3. Now you must ask me then what I should do with these 3 equations. Okay, now let us come to the point. We have obtained a relationship. Okay, we have to obtain a relationship where ni is a function of epsilon I. Okay, so this is our destination, this is our desire. What? Now we have to obtain a relationship where ni is a function of epsilon I. Yes, obviously. Then let us introduce 2 arbitrary multiples alpha and beta. These 2 are very important. In the next lecture I am going to discuss the different types of particles. Apart from the classical particles, we are also going to discuss the bosons and fermions. In those cases, in their distribution laws, alpha and beta are playing very important role. Okay, particularly beta. Beta is very important. Beta, as you know, that beta is the 1 by kt, and we have to mention that beta can be derived as to be 1 by kt, isn't it? And that is also known as the modulus of distribution, isn't it? So this alpha and beta, these 2 are arbitrary multiples. That means we have to multiply them. Multiply with what? Now alpha to be multiplied with equation 2 and beta to be multiplied with equation 3. Now I am saying multiplying with equation. How can an multiple can be multiplied with an equation? Yes, if any side of the equation is 0, then it can be multiplied in both sides. So whatever it is, the multiplication is also 0, isn't it? So if alpha is merged with the left hand side of equation 2 and beta is merged with the left hand side of equation 3, then finally the result is again 0. Okay, and if these 2 are added with equation 1 with the left hand side of equation 1, then this addition, the addition of these 3 terms is also 0. So let us see. This is the result. Okay, this is the left hand side of equation 2. Alpha is multiplied with that. This is an arbitrary multiple. Okay, arbitrary. Beta is multiplied with the left hand side of equation 3. This was the left hand side of equation 3. And remember equation 1. This was the left hand side of equation 1. So all the terms are 0. So their summation is also 0. This is very important point. This is the climax of the derivation. Okay. So sum over I, alpha plus beta epsilon plus ln ni, and then dn I as common, this is also equal to 0. Okay. Now we have two terms equal to 0. Either the term within the bracket equals to 0 or this dni equals to 0. But you know that dni is not equal to 0 because ni is a variable, so dni cannot be 0. So this must have to be 0 because multiplication of two terms, if any one is not equal to 0, then other one must have to be 0. So the other term is this one. Okay. And you need not put the summation sign here because if this one is 0, then its summation is also 0. So you need not put the summation sign here. Therefore you can directly write that alpha plus beta epsilon plus ln ni is equal to 0. Okay. So ni is not a constant. These are the formalities. The ni is not equal to 0, so this is equal to 0. Now we have to move from here. Alpha plus beta epsilon plus ln ni equals to 0. Okay. Then ln ni equals to minus alpha minus beta epsilon. Then ni equal to what? This will go to the exponential power. Okay. So this is exponential minus alpha minus beta epsilon. This expression is very, very, very important. Equation 4. Okay. And this expression also has been split into two terms, multiplication of two terms, e to the power minus epsilon into e to the minus beta epsilon. But the first two, ni equal to epsilon minus alpha minus beta epsilon, this is very important. This is equation number 4. And I am going to mention this equation when the classical particles will be distinguished with the bosons and the fermions. So take into account this equation also, okay, like equation 4. Now let us move further to arrive at the final form of the Boltzmann distribution law. So here we know that n equals to sum over I epsilon I, and sum over I epsilon I is nothing but the right hand side of equation 4, which is that means ni is nothing but e to the power minus alpha into e to the power minus beta epsilon I. Okay. So this summation sign is again introduced here. Okay. Now here you can write in place of ni e to the power minus alpha into e to the power minus beta epsilon along with the summation sign. Okay. And this part is independent of I. So you can take this out of the summation sign. So finally in the equation 5, the right hand side should be e to the power minus alpha sum over I e to the power minus beta epsilon. Okay. Now divide equation 5 by equation 4. So what was the left hand side of equation 5? Now the left hand side of equation 5 was ni, and the right hand side of equation 4 was n simply. Now the right hand side of equation 5 was e to the power minus alpha into e to the power minus beta epsilon I, and the same for equation 4 was e to the power minus alpha sum over I e to the power minus beta epsilon I. So we are just eliminating the arbitrary multiple alpha by dividing this way equation 5 by equation 4, and this way we can arrive up to this form. So this term is very much you are familiar with, isn't it? This is something like the what? Like the partition function, isn't it? So we have to introduce a new term, partition function, and you all know the physical significance. What about the particle function, isn't it? Now we can move further in determining the value of beta, but this is beyond the scope of this lecture. So we can directly write that this beta is, since here multiplied with energy and it has to be dimensionless, so it has to be the dimension is, it has to have the dimension of energy inverse. Okay, so beta should have the dimension of energy inverse, and it has been found to be equal to 1 by kT. This is the final form of beta. This is known as the what? Modulus of distribution, isn't it? And therefore for a non-degenerate system, the Boltzmann distribution law stands to be, this is the actually equation 6 is the Boltzmann distribution law for a non-degenerate system. This is what? This is Ni equals to n by that summation term, and then exponential minus epsilon I by kT. Instead of beta, we are writing now 1 by kT. Okay, and I am repeatedly saying that beta is 1 by kT is known as the modulus of distribution, and it has the dimension energy inverse. So energy inverse into energy equals to dimensionless, where we have to mention that this sum over I e to the power minus epsilon I by kT is f. Okay, this is known as the partition function, and you all are familiar with this term from the previous lectures. This is equation number 8. Now if Gi is the possibility of different ways of array in a particular energy level, that means Gi is the statistical weight factor or the degeneracy. Say the ith energy level has Gi number of splittings, then equation 7 can be written as, what is equation 7? This is equation 7. So just divide Ni by Gi. So Gi would go here, and here also Gi would be merged. Likewise this. Okay, so from the denominator of the left hand side of equation 8 or equation 7, Gi can be moved to the right hand side of the numerator of right hand side of equation 9. Okay, so the final expression for a degenerate system, it is Ni equals to n by f Gi exponential minus epsilon I by kT. And in that case, what should be the form of f? Now the form of f is sum over I Gi epsilon I epsilon Gi e to the power minus epsilon I by kT. Okay, this is equation 10. So we have finally arrived to the Boltzmann distribution law, what was written in the lecture number 3. Okay, this was for the degenerate, non-degenerate system, and this was for the degenerate system. The expression f, this is for the non-degenerate system, and equation 10 for the degenerate system. So keep in your mind equation 10. We have arrived up to equation number 10. Okay, because we are very soon we are going to have equation number 11, 12, etc. during the discussion of bosons and fermions. So we have arrived up to equation number 10. In the next lecture we shall start from equation number 11. So that's all for today's lecture. Hope you have a hectic journey during the derivation of this Boltzmann distribution law, but you have to do this, isn't it? So thank you, have a nice day.